Welcome to the latest in our XACC Tech Talk series and the last one for 2021. My name is Cathal McCabe from the Xilinx University program, and I'm pleased to be able to welcome our two speakers for today. Before I do that, I'd like to briefly introduce our XACC program and this series of talks for anyone who's new to these sessions. These talks are intended to highlight some of the applications and research related to the Xilinx Adaptive Compute Clusters program. The program is a special initiative from Xilinx to support novel research in adaptive compute acceleration for high-end compute. XACC centers have been set up at partner universities around the world, consisting of compute nodes enabled with Xilinx Alveo hardware. Participants in the XACC program can access these nodes remotely for their own research. So if you are a researcher working in high-end compute and related fields, we invite you to apply to join the program, and you can find details on the webpage shown on the screen. Our first speaker today is Dr. Kachris from InAccel. He will present on the InAccel framework that can be used for deploying, scaling, and managing Alveo-type hardware resources in a cluster. So Chris, over to you. You can go ahead and take the screen share. And please post any questions in the Q&A, and we'll try to address those at the end of each presentation. If you would like to discuss anything in more detail, I will refer you to the XACC program, which is a user community intended for these types of discussions. You can get in contact with the speakers and other like-minded researchers working on adaptive compute. We have a Slack workspace, a user group, meetings, and events.
Thank you, Cathal. Thank you very much, everyone. So I'm Kachris. I'm co-founder of InAccel together with Elias Koromilas and Yannis Tamelos. And on these slides, I would like to bring in your attention what the technologies that we have developed, that it will make much easier the deployment and scaling of application on FPGA clusters, right? So, okay. So here is the outline. So first of all, we are going to present how we try to make much easier the deployment and the scaling of application on multiple FPGAs, on multiple Alveo cards, even if it is different kind of Alveo cards on the same server. Then I'm going to discuss a little bit about how we manage to make much easier the sharing of the resources, much easier, especially when we're talking about universities that they want to share some of the FPGAs among several students, right? And then I'm going to present some of the work that we have done regarding the deployment and scaling maybe of Vitis libraries and the Vitis AI, of the Xilinx Vitis AI, right? So, so if I can summarize the whole presentation, is how we can go efficiently from a single application deployed on a single FPGA card, how we can move on a multi-tenant deployment of on an FPGA cluster, right? So how we can move to a, let's say, a cloud-native deployment of FPGAs in the same way that it is done with other processing platforms like CPUs, right? So you know that with CPUs, it's much easier when you have multiple tenants, multiple users, and they want to deploy their application on a cluster of CPUs, right? Whether it is a multi-core CPU or whether it is a multiple CPU on a Kubernetes cluster, right? So we try to, let's say, to make as simple as it is in the CPU world, the deployment and scaling of application on FPGA cluster, right? So the main point is how we are big fans of the Xilinx cluster, right? It's really very helpful, both for the students, for the researchers, for the industry. I think this is a great platform that allows somebody to experiment on not only on a singular Alveo card, but on a heterogeneous deployment of Alveo card, right? So we are users of the Xilinx cluster, and we try to make some technology that it will make much easier how you can utilize the available resources on this cluster, right? So what we are going to present is we're going to present some tools, let's say a toolbox that makes much easier if you want if you have a single application and you're going to deploy it on multiple FPGAs, even if these Alveo cards are different, how you can make much easier the deployment. Okay. So the first problem that we try to address is how we can make much easier the integration with higher level frameworks, right? So we wanted to make as simple as it is in the CPU world, to invoke a simple functions that we want to accelerate, right? So the first thing that we had to do is we had to decouple the bitstream from the application, right? So we had to decouple the hardware guy from the software guy. So the software developer from the hardware developer. So what we have done is that we try to have two different flows, right? So you can use the familiar tool flow from Xilinx to develop the bitstream. And then once you have the bitstream available, then we try to make an integrated framework that the software developer will not need to know anything about the bitstream, the memory management, etc. Right? So how we did that? So once you have the bitstream available, once you have generated the bitstream, you can also develop a JSON file, and this JSON file can describe all the details about the bitstream. Right? So we have extracted some of this metadata from the bitstream. For example, the bitstream details, what kind of a bitstream, what kind of a function it does, the platform details, which platform it is, if it is an Alveo U280, U50, U200, etc., which version of the firmware you are using. And then you can annotate this JSON file with additional data regarding the kernel file, right? So you can include details about the functions that you are going to use, right? So for example, this is the case about an encryption kernel, and you are going to present which of this data is an input, which of this is an output, etc. So the only thing that then the software developer will need is all this metadata regarding how you invoke this function, right? So once the software developer has this information, the only thing that he needs to do is just invoke the function in the same way that he will do it in a software development flow, right? So the only thing that he needs to know, the developer, is what are the functions, right? The functions inside the kernels, and what are the arguments for this function. And that's all that they need to know in order to make it, to deploy it. Then what you can then do is that if you have multiple FPGA or multiple Alveo cards available, for example, in the case of the Xilinx cluster, you can generate the bitstreams for all of the available platforms, right? So you can generate the bitstream for a U200, a U250, U280, even for AWS. And then the software developer does not need anymore to specify what exactly is the bitstream file, which exact board is he going to use, etc. Right? So that makes much easier the deployment. And also we have generated this CLI interface that allows you to control the bitstream. Right, so you can have this a local repository, and then in this local repository you can copy a bitstream file from the InAccel repository. You can copy bitstream from Xilinx, from the Vitis libraries, etc. So you can make your own mix of different kind of bits. Right. And then this makes much easier once you have the bitstream available. This makes much easier the programming and the deployment of FPGAs, because you just need to call this function that you want to accelerate, to offload, and then you just write InAccel submit and the name of the function, that it will be offloaded to the specific kernel. Okay, so I think that that makes much easier the life of the software developer, right? So imagine if the software developer had to explicitly specify in C++ or in Python in which exact CPU core the function will run, right? So we try to do the same abstraction. So the software developer does not need to know anything about which FPGAs it will run. He just calls the function, and depending on the available FPGA resources, it will automatically configure the FPGAs with the right bits, right? So the benefit of this approach is that the software framework look much closer to a CPU-only application, right? So you can see here that when you call the function, it's the same way that you call it in software. The only thing that it says is how you allocate the memory. That in that case, you have to allocate the memory using the InAccel allocation. So this is the only difference. Right, so one advantage of this approach is that it makes much easier the scaling of your application on multiple FPGA cards, on multiple Alveo cards, even if these cards are different. Even if you have, let's say, one Alveo U250 and one Alveo U280, and you want to scale your application on multiple, on both of these FPGAs, you don't need to do manual distribution of the workload, or you don't need to specify which data will go in which FPGA. Right. So in order to achieve this, we had to add one more layer, right, on this between the application and the FPGA drivers. So here, this is the abstraction layer, the resource isolation, that allows to abstract away the FPGA resources. So that means that the application do not need to talk directly to the FPGA drivers or the FPGA runtime system, but they just send the request, the function that they want to accelerate in this abstraction layer. And this abstraction layer then dispatches these functions to the available FPGA resources. Right, so it serves like an operating system. It's not exactly an operating system, not a virtualization, but it serves like this abstraction layer that allows much simpler deployment, right? So here you can see the block diagram of this abstraction layer. We call it Coral Resource Manager, in which you can see that you can have different kinds of applications or containers or pods that they send this request to this server, to this Coral, and then the Coral performs the scheduling and the orchestration of the FPGA's resources, and then it will communicate with the Xilinx drivers, with the Xilinx runtime system, right? So basically what it does, it communicates with the Bitstream Repository in order to perform the configuration of the Alveo boards, right? And then, of course, it performs the scheduling, the serialization of the request for multiple applications, and the dispatch of this request to the available FPGA resource, right? And an interesting additional tool that we have is this FPGA monitoring tool that I will show you later, that you can see also what is happening inside the FPGA. So this can be used both in order to distribute your workload on multiple kernels, right? Supposing that you have 4 kernels, 8 kernels in a single Alveo board. This allows you to just send requests to the Coral manager, and the Coral manager will automatically dispatch these functions to the available kernels. And it can also be used on a higher level parallelism, meaning that you can call as many times as you want these specific functions that you want to accelerate, and the Coral manager will automatically dispatch these functions to the available FPGA resources, right? So you have here the Bitstream repository. So every time that you call a specific function, the InAccel will program one of the FPGAs, and if one of the FPGAs is full, cannot accept any more requests, it will configure a second FPGA and a third FPGA, and it will automatically fetch the right bitstream for this FPGA. Of course, you need to have developed the bitstream using the familiar design flow from Xilinx, right? So that makes much easier to deploy your application on multiple FPGA cards, and I think this is very useful, especially in the case of the Xilinx cluster, right? So if you have managed to make a virtual machine, you first need to ask a virtual machine to have let's say 2 or 3 FPGA cards from the Xilinx cluster, and once you have this virtual machine with these 2 or 3 Alveo cards, then using the Coral manager and the InAccel manager, you can automatically dispatch your workload and distribute the workload to the available FPGAs. Right. So what we did is that we first experimented with Keras, with ResNet 50. Right. So In that case, the only modification is that we had to you have to import the InAccel Keras application from ResNet 50, right? And then you can first test it on a single Alveo cards. So this is what we did. We first tested on a single Alveo cards. You get some throughput. In this case, it was around 3,000 frames per second. And then without having to change your code, the only thing that you need to change is in this case, it was in a Kubernetes cluster. In this case, you just specify that you are going to use 2 Alveo cards. In that case, it was 2 U250 cards. And then you automatically can manage to increase the throughput of your application, right? Without having to rewrite your code at all. The rest of the code remained the same. And a nice demonstration of this approach was a paper that we developed with Xilinx. Actually, Xilinx used Coral in this case in order to show how an application that it was deployed on 2 FPGAs can use this Coral manager in order to make much easier the deployment. Right? In that case, Xilinx had developed a very nice, very high performance inference engine that it was deployed on 2 FPGA cards. And we developed a custom runtime system that enabled the initialization and the configuration of this platform and the runtime synchronization between the accelerator segments. Right. So that means with this abstraction layer, we allowed the host, the software developer, to see the context of 2 devices in a unified way. Right. So if I can rephrase it, so the design was deployed on 2 FPGAs. Right. In that case, it was 2 FPGAs, and there were several ways that it could communicate through UDP, through the typical Ethernet communication, etc. But the software developer, using this abstraction layer, managed to see it as an integrated component, as one component. Right? And with this approach, we also managed to show it was, I think, the first results on MLPerf that showed how ResNet 50 can be deployed on a cluster of FPGAs. Right. So in that case, you can see how we used the Xilinx cluster. In that case, it was from ETH Zurich. And then we managed to run ResNet 50 and get some measurements and publish these results on MLPerf results. Right? Okay, so now the second thing that is very interesting is how you can share your resources among several users, for example, or multiple threads or multiple applications. So this was a problem that we also faced in Technical University of Athens, right? So we had a couple of Alveo cards, and we wanted to do some lab experiment or want to do some teaching about the FPGAs. And the hard part is how you can share this FPGA resources among several students, undergraduate students or graduate students, etc. So this abstraction layer with Coral allows you multiple users to communicate with the Coral, and then the Coral will try to do the resource allocation of this request to the available FPGA resources. So no need anymore, just the users, the students to call each other. Okay, now I want to have access to U280. Now I want to have access to U50, etc. So all of these users, right? So we did the experiment with around 50 students. All of the students could be able to share one of the FPGA resources, right? Of course, the performance is affected in that case, but it was only for teaching experience to see how they can run their own applications on FPGA boards, right? And on top of that, we have also developed this Coral monitor that it is also very useful. Either you have a cluster or even if you have one FPGA card in which you can have let's say, a bird view or a high-level overview of what is happening inside the FPGA. So here you can see all the information about the Xilinx cluster, the Xilinx FPGA board, what is the version of the firmware, the temperature, the power. Some of these are, of course, metadata that we get from the Xilinx runtime system, right? And then you can get also information about the DTR, the memory information. And on top of that, using the Coral, you can see also, you can also get some metrics about the time it takes to execute some of this function on the FPGA, the transfer time it takes from the DTR to the FPGA, the transfer time from the DTR back to the FPGA. And you can see also from different kind of kernels and for different kind of Alveo cards, right? So this is a nice add-on that you can use. And of course, as I said, the main advantage of this one is that you can have multiple applications. In that case, we saw, for example, 2 Keras applications deployed on a single FPGA, or you can have multiple applications, 2 Keras applications deployed on 2 FPGAs on 2 Alveo boards, right? And you don't have to anymore to do a manual allocation of the resources or a manual distribution of the work, right? So just to demonstrate the functionality of this technology, we decided to take the Vitis libraries, some of the Vitis libraries, and try to make as many Bitstream available as we could, right? So we try to generate most of the Vitis library in order to be available in the Bitstream repository. So our framework, of course, is fully compatible with all the Xilinx Vitis library and all of the available Alveo cards, right? So what we did is that we developed some of the, we generated the Bitstream from some of the Vitis libraries, and we uploaded into the InAccel repository, the Bitstream repository, and then we developed a Jupyter Hub. That this Jupyter Hub allowed multiple users to be able to load some of these Vitis libraries and execute them on a cluster of Alveo cards, right? Just to mention that it was the Jupyter Hub. It was encouraged by the Xilinx University program with Cathal and Patrick Lysett, etc. Just to give the credits on this one, right? That it was encouraged by the Xilinx University. Right, so in this case, we had multiple students, for example, to be able to log into a Jupyter Hub and then call some of these functions from the Vitis libraries, and you can also test it on your own, right? So you can go to studio.inaccel.com and you can test it and run some of the Vitis library for compression, encryption, vision, computer vision, and you will see that it will automatically deployed on this on a cluster, on a small cluster that we have here, right? So the idea about the Jupyter Hub is that all of these users are authenticated to Jupyter Hub, and then we use the InAccel Coral Manager in order to dispatch this workload to the available FPGA resource. Right. And the only change that we need to do in the source code is, of course, the InAccel. The only thing that we change is just add InAccel dot, and then, of course, the Vitis library. In that case, it was the Vitis fintech library. So as I mentioned, this was very useful for a university. We tested in University of Athens, in the Moxtus University, etc., in other universities. So in that case, you can have some undergraduate students in which they can have shared access to one of the FPGA cards. And of course, this will affect the overall performance, right? But then you can have also researchers that they will have exclusive access to the FPGA resource, and then they can run the experiments for the papers, etc., without affecting the performance of it. Right? Okay, so this is all right. And the final thing that we wanted to share with you, this is a very recent development, is that we also developed a custom runtime system for the Vitis AI library. So we tried to integrate the VAR, the Vitis AI runtime system, with the InAccel Coral in order to make available all of these advantages for the Vitis AI platform. Right. So the Coral API and the InAccel Coral remained almost the same, and we developed this custom runtime system that allows to connect the Coral with the Xilinx runtime system, and specifically with the Vitis AI runtime system. What is the benefit of this one is that it can make much easier the deployment of the Vitis AI. Just to give you an example, you can go to Hugging Face /spaces in InAccel ResNet 50, and then you can see how we have tested, for example, ResNet 50 and YOLO v3, in which you can experiment with this Vitis AI library with the performance and latency, etc. And you can see how this is Hugging Face is a very popular framework of these spaces. So you can see how you can use the Hugging Face as a front end, as the graphical user front end, and then as a backend, it is running on FPGAs that it is on our server here at InAccel, right? But the front end, you can use any front end that you want, right? So you can use Hugging Face, you can use Jupyter Hub, you can use any kind of front end, and then using the InAccel, you can integrate it with a cluster, whether this is the Xilinx cluster, the academic cluster, or whether this is your cluster, your local cluster, right? So the bottom line is that the technology that we have developed allows much simpler deployment of FPGA cards with a wide, let's say, portfolio of applications, like whether it is this for machine learning, like scikit-learn, Apache Spark, Keras, etc., or whether it is DevOps tools like Ranger, Kubernetes, Knative, etc. Right? So just to give you an example, we have also developed this FPGA operator, it's a Helm chart, right? That allows much easier deployment of FPGAs in a Kubernetes cluster and automates the task related to bootstrapping of FPGAs. Okay, so this is how you can install FPGA on a Kubernetes cluster. You just call the Helm commands, and with just 2 commands, you can deploy your FPGAs on Kubernetes. Right, so just to give you an example on this, one of the projects that we are participating on, the European project, is the Morphemic that allows multi-cloud deployment, and we are contributing on this project. For example, in this case, trying to provide the tools that allows FPGAs to be deployed on multiple clouds. It allows some automatic adaptation in this case. Right. So you can read more on docs.inaccel.com, and of course you can test it for free here at studio.inaccel.com. And of course we have, we provide a free license for the universities. So any university that is interested to use some of these tools is for free. Right? So here is the summarization. Okay, we saw the InAccel monitor. Here is the InAccel FPGA manager. You can test it on the studio.inaccel, and you can see the repository of available bitstream at store.inaccel.com. Right. So, Cathal, I think it was in time, right? So I left some time for questions.
Yeah, that's great, Chris. Thanks very much for a great talk. I'm concerned we're not going to have time for all the questions that are coming in, but perhaps you can answer a couple in the chat. Maybe if I can just take one question, and this I'll maybe put 2 together. So there's a question, somebody asking about load balancing on different FPGA models, and then somebody asking about comments on heterogeneity or homogeneity of the FPGA boards versus the overall execution time of the applications. Maybe, I know that might be difficult to parse live. Maybe you could say a couple of words on the load balancing, and perhaps you could follow up on the chat during the next presentation.
Yes. Yes, right. So the load balancing is correct, meaning that we don't have any mechanism that allows let's say the fair distribution, but it works like that. So the requests are sent to the Coral manager, and it will just distribute the workload in the available FPGA boards. And if one of the FPGA boards, the queue is full, then it will try the second FPGA or the third FPGA. So this is how the load balancing is working, right? So it will try to see the first FPGA is available, and if not, it will try to send it to the second FPGA and the third FPGA, etc., until it finds one of the FPGAs to be available.
Okay, thanks, Chris.